All right, so today's warm up. All right. We are going to see, as you can see, the agenda today is polar coordinates with double integral. So let's see exactly how that's going to come up. So to get us started, I'm going to sketch a region for you. So for the region B, how can you split it up into subregions of the same type, Remember, you might want to take out the little packet with all the visuals. So here's the region I have for you. Actually, I think I have it in your visuals. Let me see. Did I put it on there? Oh, I did. Okay. Whoops. So it's this one right here. You have this region here, the orange part, or I guess I called it R. Think about how can we split up region R. Notice that if you try to do it of type 1, right? If I try to do it from here of type 1, it's going to bound with Y within the smaller circle and then this higher circle. But if I do it for X values over here, now Y is going to be bounded below by a different curve, not the small circle. So this region itself is neither of type 1, neither of type 2. Because if I try to do type 2, it's definitely going to be bounded above by something else here, versus if I do it up here, it's going to be bounded above by something else over here. Okay, so these are the difficult regions. So yes, I want you guys to kind of, it's like a puzzle. Draw it on your notes, break it up. I'm going to walk around. Oh yeah, break it up. And then at the same time, pass up your homework. Homework 16.
I was actually wondering, how come when we have like a V shape, break it up instead of just using the absolute value?
When you have like a region like this, what's on top, like that?
Like, or even if it's bounded on top, like why we don't use the absolute value for the actual V.
Ask that again once we discuss the line. Yeah.
I'm sure there's a good reason.
Oh, I guess the short answer is differentiating the absolute value is complicated.
Kind of what I'm saying.
That's the short answer. Homework? Homework, there's 16. All right, guys. Pick your brain a little bit. Oh, and then I was wrong. So we're gonna see. The last one's short. Though. The last one's short. Surface area. Last one's short. Polar ones are hard. All right, guys. Just check in with your groups. See if you guys can kind of see how you're gonna divide this here. I'm gonna pass around some homework.
Yes.
Because you can't assume that the outside's the same. Because remember, this is no. It's the exact same thing. Because you can't do 2 multiplied by the integral there because you don't know that the z is the same. But you don't know that the z is the same. You don't know that the z is the same. You can do that for account 1 and
Here, I got an extra one.
Yeah, but you're still missing a piece. So you have the left piece that's bounded by the x-axis. I hope that's actually probably won't work.
All right, guys, let's see. So let's say we wanted to split it up as type 1. I want to split up all the subregions so that they're all going to be of type 1. Is that possible? What do you guys think? Yeah. Here's some yes. Okay. So if I'm going to split it up and so that each subregion is of type 1, where did you guys split it up? First corner on the inside and just straight up? Okay, so you want this, and then I'm guessing you did the same thing over here? All right, so you want like that. So then you would call this like R1, R2, and then R3. Okay. What would Y be bounded below by here? I guess for R1, let me do it over here. So for type 1, R1 here, Y is bounded below by what? 0. This guy right here, right? It's bounded below by this bad boy. And then as Y goes up, it's going to be bounded below by the top. But now the question is, what is the top? You see that? The top is this circle right here, right? So what would you have to do to this equation? You would have to isolate the Y here. So you would get square root, you would get 4 minus x squared, and then when you square root, you're going to get plus or minus, but you're going to use minus. Plus, because Y is positive. So you're going to use a positive square root. So then Y would be bounded above by that curve, which is the upper part of the circle, 4 minus x squared for R2. Okay? We don't have the x values, so let's ignore those for now. But the x values that you would use are whatever. I guess let's make them up. This is a circle. Oh yeah, we do. This is a circle of radius 1, and this is a circle of radius 2. So then this is minus 1 and minus 2. 1 and 2. So then x will be bounded by what and what? For region 1.
Negative 1 is negative 2 to negative.
Negative, oh yeah, negative 2 and negative 1. That. Cool. All right, what about region R2? What is Y bounded below by here? Is it going all the way down to 0? No, the lowest it goes is this curve right here, right? So if you isolate Y again, you're going to get 1 minus the square root of x squared. So then Y would be bounded below by what, and then above by what? You guys tell me. What's the lower one? Positive root 1 minus x squared, the smaller circle, and then it's bounded above by which one? The bigger circle. That's right. But now here x is between what and what? Negative 1 to 1. Negative 1 to 1. Good. And then for R2, what's Y bounded below by? R3. Sorry, for R3, Y is bounded below by 0, and it goes all the way up to the positive square root. But now x is between what and what? 1 and 2. 1 and 2. That's right. So that means that, yeah, questions?
Oh, I was gonna say, is it possible to take the integral of the big circle and subtract the little circle?
You can do that, yes. You can do that. Yeah, so what Ethan was saying was, what if instead I consider this region of this big circle, call that D, and then do the integral over D, and then get the little circle, call that, I'll call it C here. Do this integral over this one, since this is of type 1, and this is also of type 1. And then you can subtract those volumes. Because this would be the volume over the entire hemisphere. This would be the volume over the little hemisphere. But since you're looking for the volume of this guy, you can just subtract those. That's another way you could do it. Yeah. Regardless, you have to do multiple integrals. Okay, that's kind of the story here. And regardless, this guy here, y would still be bounded above by this guy, and y would be bounded above by this guy. So no matter what, your integrals are not going to be able to avoid square root functions, which nobody likes in an integral, because trig sub creeps its way in there. Okay? So the point of today's section with polar coordinates is whenever I have circular regions, my integrals on x and y coordinates can get pretty complicated. Either because the integral will be complicated, because the functions are complicated, or because I have to do all this breaking down of regions to make it work. So what we're going to try to do today is, we're going to learn how to use polar coordinates so we can do one integral using this region, and the bounds are actually just going to be numbers. Okay? So that's kind of why we're going to do this, to make it a lot easier for ourselves. All right. Any other questions? All right. Okay, so let's see how we're going to do this. Let's check it out. All right. All right, so we're going to jump to section 15.3, double integrals in polar coordinates. But you guys probably haven't messed around with polar coordinates in a more advanced way than I think Calc 2, right? When you guys learn polar coordinates, maybe pre-calculus, you covered it?
Yeah.
But I know it's been a minute.
It's been at the end of the class.
Yeah, right? So before we actually jump into all that, let's do a short polar coordinate review, okay? So let's quickly review polar coordinates. And some useful formulas that you have to remember. So visually, you have, this still lives on the xy plane, and you have a point which has coordinates xy. But remember that for polar coordinates, the way you plotted a point was you always started at the positive x-axis, and then you had an imaginary radius that would rotate in the counterclockwise direction. And then you would rotate it so that that radius points towards that point. And so then you had this kind of imaginary radius right here. This was the angle theta of rotation. And then the length of that radius, we're going to call it r. Okay? And so then now in in polar coordinates, that point, we call it r comma theta. So I want you guys to practice envisioning like a laser. That's going to be helpful for finding bounds later. You have a laser, and your laser is going to stop right when the laser hits the point. And then the distance from the origin to here, that length, that's what we're going to call R. Okay? But then from there, you used a small little right triangle there. This length was the x coordinate length, and then this height was the y coordinate length. So then you did a little bit of trig, and then you learned that you can write x as r cosine theta, and you can write y as r sine theta. Okay? What did the Pythagorean theorem tell you? x squared plus y squared equals the length of this hypotenuse, which is r squared. So that was the relationship. These are what's called conversion equations. So polar to rectangular conversion equations. It'll help you go from one to the other. So that part you kind of already have been doing. What you haven't been doing is you probably forgot how to graph a polar curve. So that's what I want to show you with you. Okay? So let's remember how you graph a polar curve. So let's see. So let's graph, let's do a polar curves. And then you know how normally you have y as a function of x? You remember that for polar curves, you normally have r as a function of theta. Okay? And so we wanted to look at this example. Let's remember how to graph r equals 2 cosine theta. Let's see what that looks like. So the homework's going to have you do two things. One is graphing and plotting points, just to review. And the other one is we're going to rewrite this polar equation in what's called rectangular coordinates. So it turns into an xy equation. Let's do the graphing part first, though. So let's make a little table so you remember how to do all this. What's the input variable? Theta. And then the output variable is going to be r. So because we're used to the special angles, let's just do a few special angles. Let's do 0, pi over 4, pi over 2, 3 pi over 4, and then pi. Let's just do those for now. So you plug in 0 into cosine. What's cosine of 0? 1. So that's just 2. And then what's cosine of pi over 4? Root 2 over 2. So the 2's cancel, and it just becomes root 2, which did I put is about, root 2 is about 1.4 units. What's cosine of pi over 2? 0, so that's just 0. All right, cosine of 3 pi over 4. Negative root 2 over 2, yeah. Negative root 2 over 2, so it just becomes negative root 2. So it's about negative 1.4. And then cosine of pi is negative 1, so we get negative 2. Okay, so now plotting these points, 0, 2, pi over 4, root 2, that is where it gets it's different. You probably haven't done that in a while. So this is how you're going to want to do it. Think of that laser, okay? Think of that laser. So this says when your laser is pointing 0 radians, stretch it 2 units out, okay? Stretch it 2 units out. So let's say this is 1, 2, 1, 2, 1, 2, 1, 2. So if my laser is pointing 0 radians from here, and then I stretch it out 2 units, that's going to give me this point right here. That's 0, 2 in polar coordinates. Okay? Then for the next point, you rotate your laser pi over 4 radians, so 45 degrees, and then it's going to stretch out root 2, which is about 1.4. Right? So let's see. So it's going to be 45. This is about 1, and then a little bit more. So it'll be like somewhere here. Okay? That's how you would plot that point. So it's kind of like it's shot out pi over 4 radians, and it's stretched 1.4 units-ish. Then you got, this one's weird. Then you rotate pi over 2, but how far does your laser stretch out? 0 units. So where is that point? Origin. It's going to be in the origin. So notice that it's possible to have a point at the origin with a non-zero angle. Okay? That's going to come up later on. All right, then you get the laser, you rotate it 3 pi over 4, which is this direction. But do you see how r is negative? You guys remember what to do with that? Does it stretch in the direction of the angle? It's going to stretch in the opposite direction of the angle. So it's going to actually shoot backwards, 1.4 units away. So if it stretches here, but it's actually going to go backwards. So it's going to be like right below that point right there. Does that kind of ring a bell?
Is there a 5-second explanation of why it goes 180 on that?
I think what it was is that when your r is negative, like for example, the point at pi over 4, you plug in pi over 4 here, you plug in pi over 4 here. The fact that r is negative is going to it switches the sign of your coordinates here. So for example, at pi over 4, what is r here? R is negative root 2, right? For this guy here, r is negative root 2, and theta is 3 pi over 4. That's going to be negative root 2, but since cosine is negative root 2 over 2, notice that instead of x being a negative coordinate, the fact that r is negative switches its sign, and now it's going to become negative 1. Okay, that becomes positive 2 over 2. So that means that instead of being in the third quadrant, when r is negative, it actually made it go in the opposite direction. And then the same thing with y. Sine of 3 pi over 4, that's negative root 2. The sine of 3 pi over 4 is positive root 2 over 2. So instead of sine being a positive coordinate, since r is negative, it flipped the sign of it. So now instead of being a positive y coordinate, it swapped it. Yeah. And so when r is negative, wherever the point is supposed to be for the angle, it swaps the coordinates. It flips it. So that will force it to go backwards. So if here x is negative and y is positive. Oh yes, sorry. Thank you. Yeah, so if the angle was over here, let's say it was like 5 pi over 4, x is negative and y is negative, but if I flip the sign of both of those coordinates, it'll force it to go backwards over here. Okay, that's my 5-second. Okay. Yeah. Okay, so where were we? We're here, and then we had at pi. So you rotate your laser pi radians. But since r is negative, instead of stretching 2 units towards pi, you stretch 2 units opposite of that angle. So that's going to take you back here.
Is it negative 2?
It is negative 2. It is negative 2. Here, let me take another drink of my. Maybe that'll help me. Yes, thank you. It's negative 2. So now the question is like, it might be a little bit harder to see what the graph of this might look like. So then what we do, I mean, we can keep plugging in more points. But notice that when we got to pi, it kind of seems to repeat because it ended up back where we started. Okay. So now let's turn this equation into a rectangular equation. Okay. So let's convert r equals, what is it? 2 cosine theta into rectangular coordinates. So this is where the algebra comes in. You're going to want to use your conversion equations. Okay. You're going to have to do a little bit of manipulation. Do you guys see how there's a cosine here? There's a cosine here. But if there was an r in front of it, then I can swap it for an x. right? So what can we do to this equation so that there's an r in front of it? Exactly, just multiply both sides by r, and then we get r squared is equal to r cosine theta. And then notice that not only that, we got an r squared. So what can I swap the r squared so that it's in terms of x's and y's? X squared plus y squared. So I turn it into x squared plus y squared. And what is the r cosine theta going to be swapped for? 2x. So notice now I now have an equation of just rectangular coordinates. It kind of wants to look like a circle, but it does not have, like a number. You guys remember from here algebraically what you can try to do? You're going to want to use your favorite method called completing the square. If you remember if that is, if not, let's do a short review. So you're going to minus the 2x to both sides. You're going to minus the x to both sides. I'm going to purposely put it here.
That's why I'm on this one.
Yeah. I minus the 2x here, minus the 2x here, so that becomes 0. But to complete the square, I'm going to complete the square of the x coordinate. Remember that to complete the square, you had x squared plus bx plus the magical b over 2 squared becomes x plus b over 2 squared. From pre-calc, it's been a minute. Okay, but basically you want to add this guy to complete the square and make it into a perfect square that factors. So right now the b is like the -2. Okay, so -2. So we got -2 divided by 2 squared. What is that going to become? 1. That's going to become a 1. So what you're going to have to do is add that magical 1 here. But whatever you do to one side of the equation, you must do to the other side of the equation. But now by doing that, what happens to this quadratic of x? What is it going to factor into?
X plus 1 squared.
It's going to factor into x plus 1 squared.
Oh, sorry, minus 1.
Oh, thank you, minus 1. And then we're left with a 1 over here. Does that look a little more familiar now? The circle of radius shifted 1 unit to the right. And notice that if I draw a circle centered at the point 1, 0 with radius 1, that's going to be this circle right here. Oh, damn.
Yo, that was good.
I'm proud of it. I'm proud of it. So what does that mean? That means that the graph of this polar curve is this circle that is shifted 1 unit to the right of radius 1. Okay? Any questions on the algebra here? I know it's review stuff, but it's okay. Yeah, go for it.
I think it's kind of weird how normally we have the multiplication of a circle, it's just going to be r equals 1, but now by multiplying the right side by 2 both sides, we shifted it 1 unit over. I just think it's weird.
That is weird. Yeah, I agree. Like by multiplying it, like, so let me kind of, in case you didn't get his comment. If the equation just said r equal 2, okay, you said 1, but let me leave it 2. If it said r equals 1, r equal 2, that means to graph this guy, there's no theta. So for every theta, r is equal to 2. What does that mean? That means that for every theta, r is always equal to 2. So what would the graph of that look like? Circle of radius 2, but centered at the origin. And so his comment was, he just found it funny that when you multiply by cosine, that like created a shift. Which that is pretty interesting. Okay. So I'm not gonna expect you to remember all these polar curves. So I created a little handout with a summary of them. So grab one, pass it down. Pass it down, because I know it's been a minute. Pass it down. Oh. Oh, there's only two of you guys. Yes. Other extras?
Yes, the bugs.
All right, so you guys look at these handouts. They kind of give you the general formulas for these polar curves. And so let's just do a quick play. Let's play with it super fast. Let me go to Desmos. So you have, like the one that we just did is r equals 2 cosine theta. And that's that circle right there. But what this is saying is that if I make a slider A, notice that when A is 1, the circle has diameter 1. But the bigger I make A, the bigger the diameter gets. But the circle will still touch the origin right there. It's kind of stuck there. Because at pi over 2, cosine is 0. So it'll make r 0. So it's kind of stuck there. Cool, right? If I don't have cosine, and I just have A, then you'll just always have a circle centered at the origin of radius A. Okay? And then I think they show theta. Does it do theta? I don't think it's gonna graph theta. Theta's not gonna get graphed. But basically for theta, you guys look at the top. If you make theta some radian, in this case it says radian 1, rotate your theta, and there's no r. So r could be whatever you want it to be. So that's why it turns out to just be a line. Where the angle of that line is theta. But r could stretch, r could be whatever you want it to be. So it'll force it to stay within that angle. If r is positive, it'll stretch in that direction, but if r is negative, it just stretches in the backward direction. Okay? Then you have your beautiful rose curves. Let's see, r equals, let's do the one on the bottom where it's a cosine n, let's do 5 theta. Let me do 4. Notice that it's like a petal here. How many petals do you have? 1, 2, 3, 4, 5, 6, 7, 8. So it's telling you that if n is even, you have 2 to the n petals. Okay? Again, you can just use this handout. I'm not gonna have you guys I'm not gonna stress too much about this stuff and expect you guys to remember all these facts. But if n is even, then odd, then you just have that same number of petals. Okay? So where we're headed is you might have to integrate a function over one petal only. Okay? So you're gonna have to do all this in polar coordinates. That's kind of where we're headed.
All right, so integrate one of them and then just times another.
Gotta be careful. No, we gotta be careful. You guys gotta remember, you gotta be careful what the surface above looks like. If I want to integrate, if it says to integrate the function over all the rose petals, you gotta be careful. You just can't do over one rose petal and then multiply it. Because if your function is not symmetrical, like if it's let's say a plane, the volume over this petal is not going to be the same volume over this petal. You gotta be careful. Okay, yeah, so I just wanted to show you guys that. Okay. So, here, I want you guys to kind of do a problem like this one here, just to do a quick review. Practice. So graph r equals 2 sine theta using a r theta table. Because I also want you to practice plotting points in polar coordinates. Number 2, I'll rewrite r equals 2 sine theta in rectangular coordinates. And then the third one is a little unrelated to the first two. I'm going to give you an equation in rectangular coordinates, and I want you to write y equals x in polar coordinates. Okay? So try to graph this one using a similar table like what we did here in plotting points. Then write it in rectangular coordinates like we did like with this one. And then the third one's a little bit not related to the first two. We just commute them into us. I want you to practice plotting points in polar because it's going to be important when you're bounding your regions. Like that thinking, I need you to practice it. Okay? Because yes, technically you're right. You can turn it to rectangular and see if you can graph that. Yeah. More homework on the first one? The solutions from last week's homework have been posted. Take a look. Hello, bless you. Ben, is this you? Usually use colored paper. Okay, let me leave it because I haven't given you it. That's yours. Where you put your hat? Love your hat. All right, guys, do a quick check-in. I see different circles. I see circles in different spots, so please do a quick check-in. Ben, Kevin, I'll have you guys check in. Yeah, you guys are check in. Jacob, you can check
What would that look like? Oh, okay. I was thinking right that, just instead of dividing, like, vector out, put it to one side and divide that side, we need to do on. Because the angle measure is where you still right, they're actually just where what theater you got? I have.
They have like positive X and negative X positive X. Vice versa. So it's, you know,
It's mostly logic.
it's just.
Right, it's like the alien.
You guys can check your work here. All right, so let's see. Let's take a look. Make sure this is on the video. All right, so for this bad boy here, you got an angle 0, sine is 0, so your radius is 0, so it stays at the origin. Pi over 4, you're going to get your r is √2, so that's about, again, 1.4 units, similar to what we did in the previous example. But now at pi over 2, sine is going to be 1, so it'll stay 2. But now it's going to stretch 2 units towards pi over 2. 3 pi over 4, sine is positive √2 over 2. The 2's cancel, so at 3 pi over 4, it does stretch towards 3 pi over 4. And then again, it's pi, sine is 0, so you get it back here. So notice this time you get a circle towards the y-axis. Okay? So when it's 2 cosine theta, it's on the x-axis. When it's 2 sine theta, it's on the y-axis. Okay? write this in rectangular coordinates, it's very similar to the previous problem we did, except that now you're going to get 2y. So when you complete the square, you're going to get y minus 1 squared. So notice it's a circle of radius 1 whose center is at 0, 1. Okay. Questions on those two? Good? Okay. Very similar, right, to the previous problem. All right, this one's different. So here, notice that if we were just to graph this, that is just this line, the line that has intercept 0 and slope 1/1. Right, y equals x. It's just that diagonal line. But in polar, you convert these to r sine theta, r cosine theta, and then notice we can divide both sides by r. So we get sine theta, cosine theta, and maybe some of you guys were like, uh-oh, what do I do from there? So we can rewrite it by dividing both sides by cosine, so that this becomes tangent of theta is equal to 1. When is tangent of theta equal to 1? When theta equals pi over 4. Or negative pi over 4. No. Pi over 4, more angles. I think it's negative 3 pi over 4 or 5 pi over, yeah, it's a shitload of angles. But the smallest positive one is pi over 4. So notice this kind of goes with what I was saying earlier. You rotate your theta by pi over 4, and since the equation, it's a little weird. Since the equation doesn't have any r's in it, r can vary, and it can just stretch that laser in all infinite directions. So it creates that infinite long line, as long as the angle stays within pi over 4. Cool? Questions on that? Okay, so that's our review, the polar coordinates. Okay? Let's bring in your friend integration. All right, so hopefully the thinking of like all this review here kind of helped you remember how to plot points and polar coordinates and all that good stuff. Okay. So let's bring in a double interval now. So double integrals in polar coordinates. So here's basically the goal that we want. The goal is we're going to have a region in rectangular coordinates, and then you have a function in rectangular coordinates. I want to be able to express a double integral with some region. We're going to call it, what do we call it here? We call it R. And we want to do it so that it's in polar coordinates. And so therefore, I have to convert all of my x's into r cosine thetas and all my y's into r sine thetas. All right, so let me show you the game plan. Go like this. All right, so here's the game plan. These regions that we saw in the warm-up are challenging to bound, are always going to be most of the time are curvy, that are circular, they involve circular curves. So it'll be some kind of region that looks like this, okay? We're going to call this a polar rectangle because R will be a length all the way up to B length. So notice that R will be a constant equal some constant A or some constant B. Okay? Those are the bounds for R. And your theta is always going to be between some angle alpha and then some angle beta. Okay? Remember that laser I told you guys to imagine? I'm at the origin, I shoot the laser. As I move my laser, the smallest angle for theta is alpha, and the smallest angle for theta is beta. You want your laser to always hit the region. Somewhere, at some point. Okay? We're finding volume above this guy. There's a surface. And we're going to find the volume between the surface and that rectangular polar rectangle. So we're going to do the same thing we did with a normal rectangle. We're going to break up our polar rectangle into small little polar rectangles. And I'm going to actually draw this. I'm just showing you kind of the game plan. We're going to pick a point in this smaller sub-rectangle that we're going to call Rij. We're going to break up our R here, our R's, from alpha to B. We're going to break up our values of R into sub-little intervals like this. Okay? With this interval here, it goes from Ri minus 1 to Ri. So we're going to call this the ith R interval. Okay? Your thetas, you're going to split them also into intervals, like this. So that this is the angle theta j minus 1, and then the angle theta j. So we're going to call that the j theta. Okay? Each of these intervals, they're going to split up theta into a width of delta theta, and we're going to split up the intervals for R and call them delta R, which is not shown here, but we're going to write it down. Pick a point, like we did with the rectangles, plug in that point into your function, give you your z value, and then find the volume of that little box within that rectangle. Just like we did with the rectangle. Okay, yeah, and then I'll show you more stuff from there. There you go. That's a zoomed in version of that. Oops, careful. Does that sound good for the game plan? We're gonna plug in for each of these little sub-rectangles. You're gonna plug in one of those points, our polar points, Ri star theta j star. Plug it into that. Get a volume for all those little boxes. Do that for all those little boxes, and then add up all those volumes. Give you an estimate. So it's very similar to the rectangle and we got to bring in all this stuff. All right, so that's the game plan. Let's see how we're going to do this. All right, let's see. All right, so we're gonna define a polar rectangle. R is going to contain polar points R comma theta, where R will vary from A to B, and theta is going to vary from alpha to beta. So you want to draw a picture, or you just want to go off of what you have there in this bracket. So this is our R. Here's the theta equals alpha. Here's the theta equals theta. This is what R equals A, and this is what R equals B. This next part, I'm only going to draw the sub-rectangle of each picture. You're going to get one of these little guys. One of these little guys. We're going to split R into smaller sub-rectangles, Rij. And I want to pick a point RI star theta J star within that subrectangle. With that subrectangle is the zoomed in version of what I'm going to show you here. So here, this is the angle theta J minus 1, theta J. And this is RI minus 1, RI. And then this is the point that we're taking. This point is going to be strategically picked so that it's halfway between RI and RJ and RI minus 1, and halfway between the two angles. So it's going to be smack in the middle right there. Okay? That's what we're going to call RI star and theta J star. Is that theta J? This theta is J, yeah, this guy right there. Where, again, I want my RI star, I want this guy to be strictly in between the two R lengths. So remember that when you're trying to find a number between two other numbers, you just take the average of them. We'll give you the middle value. So where RI star is 1/2 of R, how do I write it here? I minus 1 plus RI. That will guarantee it to be in the middle. And then the same thing with theta. I want the theta to be in between. So theta J star is going to be the average of theta J minus 1 plus theta J. Okay. This length from RI minus 1 to RI, that length, we're going to call that delta R. So what is it? It's just the distance between these two R's. So I just subtract RI minus 1, sorry, RI minus RI minus 1. And then our delta theta is going to be the difference of those two thetas. A lot of notation, sorry. Okay. You got the setup. Okay. Remember, picking this point, plugging it into F, we're going to plug it into F to give me your Z value. That will give you the height of that little box there. And then if I want to find the volume of the box, it's going to be the height times what? Times the area of this bad boy, right? Of the base. So the question is, how the heck did we find area? How would I find the area here? I can't just do length times width because it's not an actual rectangle. So this is what's called a sector of a circle. So let me give you another quick review. Okay? So quick review. Area of a sector of a circle. The textbook doesn't review this part, okay? So be careful.
So don't have R also. Don't have R.
Kind of, yeah. I think you got it. So let me remind you what that looks like. So if I have a circle, but I only want the area of one of its sectors. Let's say I only want this area here. Looks like a pizza slice. There's an angle between between those two secant lines, or the two radii, let's say. And let's say this is a circle of radius r. Okay? So the idea is to find the area of the sector. What you do is you say, what's the area of the circle? And then you're not taking the area of the whole circle, you're only doing the part related to this angle. So you're going to kind of do a proportion. You're going to say, I'm going to do that ratio of theta over the entire angle of a full rotation. That's kind of the idea behind it. Okay? So what we're going to say is, what out of the 2 theta radians, I'm only going to use the theta amount. So theta out of the 2 pi times the area of the circle. That's kind of like the construction for that. Okay? It's just this proportion out of the entire 2 pi times the area of the circle. But to find the area of the circle, that's just pi r squared. So then the pi's cancel. So it turns out to be 1/2 r squared times theta in radians. Okay? So that was a quick review. Okay? So that's what this area will equal. It's kind of like the circle, but it has a little bit more. So that's how you take the area of a pizza slice. Yeah, now you guys know. So measure the angle of your slice, the radius, and then you can say, oh, I ate like 10 inches squared of pizza. You should totally do that to someone. I'm gonna slap you. Okay, so how are we gonna use this to find the area of this piece here? Do you guys see how this whole big shape is a pizza slice? So what we're gonna do is find the area of the big pizza slice and minus the area of the small pizza slice. And that'll give me this guy. Okay? So this is gonna have area, which the textbook calls delta AI. AI, it's funny. Okay, so to find that area, area AI, here's what we're gonna do. We're gonna do the big pizza slice minus the little pizza slice. What is this angle here, though? What is this angle right here? What are we calling this angle right there? It's the change in this theta to this theta, right? That's this guy. Okay? So this has delta theta, has the same delta theta. How long is it from here all the way to the farthest radii? What's this radii here called? What are we labeling it? That's Ri, right? So this is Ri, or this one is Ri minus 1. Okay? That's going to give me the area of this little guy that I want. So then therefore, delta AI, if I use this formula here, it's going to be 1/2 times my length of my radii here, or my radius squared, times delta theta, the angle between those two lines. That's the area of the big guy, minus 1/2 Ri minus 1 squared delta theta. So that's pretty. Look, what can we factor out?
I squared minus
That's right. I'm gonna purposely factor out the delta theta to the right, though. Okay. So notice that it looks like this. Ah. Most of you probably won't use this in your real world jobs. But what you will use is doing complex ass shit, organizing it, figuring out what it's saying, and then telling someone what it means. That skill you will for sure learn. And you will for sure do at a job that hopefully uses your degree. Okay. Do you guys see a difference of squares? Difference of squares. So this factors into Ri plus Ri minus 1, and then Ri minus 1, delta theta. Okay? Which looks nasty. But it isn't nasty. It's actually really cool. Though that what you see there is somewhere else on the board. Yeah. These things that you see here are somewhere on the board. Yeah, where is this on the board? That's this guy. Where is this on the board? That's this guy. That's the R. That's that average value. Okay. So what ends up happening is that your delta AI, this becomes Ri star, which is that middle R value. This becomes delta R, and then that is just delta theta. Okay. So what does that mean? That means that that this subrectangle here will not have the same area as this smaller subrectangle here, which visually makes sense because these are going to be like a little smaller than these. And that's because this will be the same and this will be the same, but this is what's going to change. It like stretches the area by a factor of Ri star. The farther Ri star is from the origin, the bigger the area is going to increase. So that Ri star controls the change in the area of how it's going to grow. Okay? And that's going to be important. So because it's important, I would like you to circle it. And so notice the area of Rij changes by a factor of this Ri star value. Let me see what your picture packet looks like. Okay. So remember, this was our goal? Let's go back to our goal. This was our goal, okay? That was our goal. So we have to figure this out because of this next part here. So then now when we're trying to find the volume, we're going to plug in X, we're going to rewrite it as Ri star cosine of theta j star, because that's the R and the theta at that point. Remember, that was this point right here. So when you convert it, when you use the conversion formulas, this is the R, this is the theta that you use. So X becomes Ri star cosine theta j star, Y becomes Ri star sine of theta j star. Right? That is the point that's being plugged into the function that gives you the height of the box times the area of the box, which we just found. So times your delta AI. Cool? Is my follow? Okay. So then you add up all those subrectangles as they vary throughout the intervals of r and throughout the intervals of theta, and then you take the limit, just like we did with the rectangles discussion. But then, as we showed, delta AI has this factor of r that gets popped out. So then it gets popped out right here. So then the way we're going to define the double integral with polar coordinates is we're going to say it's still a double integral where r will vary from a to b, which is the a to b that we got here, and theta will vary from alpha to beta. All your x's become r cosine theta, all your y's become r sine theta, but here's where you got to be careful. But now, when you rewrite your double integral in polar coordinates, your dA, right there, you need to rewrite it as r, this magical r pops out. R dr d theta. You forget that r, you got the whole problem wrong. And you integrate. Okay, so just don't forget that r.
It's not just being multiplied into a function, right?
Exactly. Yeah, whatever this function is, you just distribute it. You'll notice that sometimes it's very helpful because it lets you do U substitution. Okay. And so here, I have this here, but let me write it down. So double integral in polar. So if f is continuous on a polar rectangle, R, where your R is in between A and B, and then your theta is in between alpha and beta. Then the double integral becomes R is varying from A to B, and theta is going to vary from alpha to beta. And notice your bounds are just numbers. Yeah. Okay? And then yeah, all your x's become r cosine theta, all your y's become r sine theta. But then you get that r that pops out, the r d theta. So don't forget the r. It's the one that can make the whole problem either really hard or just wrong. Say it again.
So he's using to that thing.
What did I say? It either makes it.
Really horrible or it's so completely wrong.
No, sorry. either very easy. No, I'm saying if you forget the R.
Oh.
You forget the R, then it could be really hard or just wrong. That's what I meant. Not the R fucking making it more complicated. No. It's supposed to make it easier. Yeah. Thank you. Yeah, for the clarification. And so, as you're hopefully noticing on the homework, is setting up the integral becomes really hard. Huh? The integration, that could also be kind of hard, but it's the setup here. But let's take a break. We got the setup. This is what we're going to focus on now. Okay? We're going to figure out how to do this. Let's take a break though, and then we're going to do some practice problems that I'll have you guys try as well. Come back at 2:17. Sorry for all the talking, but it was just so much of this stuff. All right, guys, here we go. So let's actually start doing some integrals here, and then go slow, do a little build-up. ask questions, pick it apart. So let's see. Let's try this bad boy out. So here's a typical homework question in this section. It'll say find the volume of the solid bounded by the plane z equals 0 and paraboloid z equals 1 minus x squared minus y squared. Okay, so we're doing volume. We've got to do double integral here. Let's sketch this the region first. Okay. Yeah, let's sketch the region D first. So let's sketch region D first. See what that's gonna look like. So let's remember those tips that I showed you guys. So try to graph anything that does not have any z's on it. Nothing has none of those. And then if it does have a z, then what do you try to do?
Z0.
Make z 0 so that you're on the xy plane, and then see if you can graph that equation, right? So this one is just z equals 0. That is the entire xy plane. But this one, let's see what happens when you set z equal to 0 on that one. So we're going to set z equal to 0. We get 0 equals 1 minus x squared minus y squared. Move x and y to the other side. And what do we end up getting? We get a circle of radius 1. And so let's see here. So that's my region D here. This is my the entire circle here. And that's it. That's all we can graph, right? So that is the region. Is that disk right here. Okay. If we were not using polar coordinates, you would have to do a type 1 or type 2. If you did type 1, you would have to do the lower bound, which is the lower part of the circle, and then the upper part of the circle. So like the warm-up, you would have to get y by itself. You would get y equals the negatives and positive square root. You see all that? The square root stuff comes in, okay? So that's why it's like, oh gosh, I don't want to do that. So instead, we're going to bring in polar coordinates. So let's convert this into polar. Okay? X squared plus y squared, what is that in polar? It's just r squared. R squared. So it's r squared is equal to 1. So if you square root both sides, you get r is equal to plus or minus 1. But if you guys look at the summary sheet for circles, it doesn't matter the scalar because it'll just still be a circle with radius 1 centered at the origin. It's just when theta is like pi over 4, if it's r equals positive 1, it stretches towards that. If r is negative 1, it just stretches behind it. But it's still the same circle, okay? So most of the time, your textbook will just use the positive one. It'll just say r equals positive. So what does that mean? That means that, do you guys see this, the entire circle boundary? That is the equation of the circle. R equals 1 in polar coordinates. So when you're going to find your bounds for R, your laser always starts at the origin. Don't do this anymore with X's and Y's, okay? For polar, your laser always starts at the origin and you shoot your laser out. I shoot my laser out. What's the farthest that it goes? 1. What's the shortest that it shrinks? 0. That's the shortest that it shrinks. Is that true for all theta? It's true for all theta, right? So notice that in polar coordinates, r is going to be bounded by 1 and 0. If I shoot my laser, does my laser touch the region for all 2 pi radians? Yeah. Yeah, right. My laser, no matter where I rotate it, it will always be touching the region. We're going to look at all kinds of examples later that to help you kind of differentiate that, okay? But for now, it's like the easier one, where it's like literally r will just go from 0 to 1, and then all the theta angles are included. Okay? So then to answer this question and to find this volume, that means I need to do this double integral. Oh. Hold on. We're not there yet. Hold on. All right, so let's just, sometimes we can graph the surface, other times it might be too hard to graph the surface. But let's put a picture here in 3D. In 3D, you have the plane z equals 0, and then you have this, it's telling you it's a paraboloid. Okay? When y is equal to 0, remember the traces and all that stuff? When y is equal to 0, what is the graph of this on the xz plane? Parabola facing shifted up 1. If x is 0, same thing. Parabola facing down, shifted up 1. So notice that your paraboloid is going to be a paraboloid shifted up 1 unit. Like that. Facing down. And where it crosses the x-axis is at this circle right here. That's where it crosses the x-axis. Okay? And so we're being asked to find the volume between this paraboloid and then that disk, this circle. Why am I bringing that up? Because what is the function of the surface? What is the function of this surface here? What do I put here as my function?
1 minus x squared minus y squared.
Is that what you're going to say, Sam?
Yeah.
Yeah, that surface, right? This guy here is just this equation here where z is isolated already. So that's what I'm going to do. So that's the guy I'm going to put here. 1 minus x squared minus y squared dA. Okay? But I don't want to bound d with x's and y's because as we discussed it, it's going to be too ugly. So we're going to convert it now and use this new stuff. We're going to convert it into polar. We're going to convert it into polar. So in polar, r is going to be bounded by 0 and 1. And then theta is going to be bounded by 0 and 2 theta. Okay? What do I have to do with the function? I got to convert it to polar. That's right. So notice, this is just going to be 1 minus r squared cosine squared minus r squared sine squared. There's a little algebra there. Sam. Exactly. Notice that I could take out the r, the minus r squared. And what is cosine squared plus sine squared? 1. This is 1. So then the function that I get here now is 1 minus r squared. That is this right here. Okay? Let me have you start. Another way that you could have done this is you could have done this. You could have taken out a negative. You could have taken out the negative, and what's x squared plus y squared in polar? R squared. So it's still 1 minus r squared. That's another way you could have done it. So there'll be different ways to turn it into polar, okay? All right, what do I do with my dA? Don't forget the r. R dr d theta. Bless you. R dr d theta. That came out from the conversion. What? And so then notice I end up with theta goes from 0 to 2 pi. R goes from 0 to 1. Let's distribute this r now, and we end up with r minus r cubed dr d theta. Way easier to integrate than if we were to stick to rectangular coordinates. It's a lot easier. Because the function's hella nice, and the bounds are just numbers. Okay? I want to show you a trick in case you haven't read the textbook yet, because I didn't have time to cover this. So in 15.1, there's this nice helpful property. So if you have a double integral with scalar bounds, sorry, my cat fell. With scalar bounds and your function that you're integrating, you can write it as a product of a function with just x and a function of just y. Like if you can factor it somehow, so there's only x's on one factor and only y's on the other factor. And then let's say x goes from A to B and y goes from C to D. But now the function itself can be written as a product of these an x function and a y function. Then there's this nice property that says I can completely separate the two integrals and do a product of the x interval and only focus on the x stuff, and then do the y interval separately, and then integrate that one like that. So it's like you can factor out the intervals. It's a very helpful fact to kind of like help you make things clean. But it's only when you have scalar bounds, and it's only when the function can be thought of as a product of the two different input values. Okay? So we're going to use that here. I have scalar bounds. I have dr d theta. Think of the r function as r minus r cubed, and think of the theta function as just 1, the number 1. So then I can split this up into just theta, 0 to 2 pi, 1 d theta, and then separately do the r on its own, r minus r cubed dr. And you're going to see that happen a lot in this section. Helpful, right? Yeah, all these little nuggets. What's the integral of 1 with respect to theta? What is it? Theta. Theta from 0 to 2 pi. So that's just going to be what? 2 pi. 2 pi minus 0, so it's just 2 pi. And then this bad boy is going to become 1/2 r squared minus 1/4 r to the 4th from 0 to 1. You plug in 1, you're gonna get 1/2 minus 1/4. What is that, a 4? Plug in 0, you just get 0. So it's just 1/4. And so then my final answer is gonna be pi over 2. Is that the area of the circle? Or is that, what is that? It's the volume of this space inside here. That's the volume. Don't forget. Okay, it's the volume. Man, these files took so long. Any questions here on the bounds?
Why is it possible?
You could see the textbook, but I'll give you a fast explanation, okay? Since I can separate this as a product, if I integrate with respect to x first, this is just a big fat constant. So I could take out that constant.
Oh, I see.
Yeah, so I take out that constant, then I'm left with, yeah, I'll just do it. So then you're left with this. From A to B, g of x dx dy, right? You integrate that, you plug in some numbers, that's just a scalar. So you factor that scalar out from that integral.
Oh.
And there it is. Yep. You can't do this if this is not scalar stuff. Like if this was from 0 to, let's say, the square root of x, then you integrate this, but when you plug that in, you're gonna have a square root of x. That's not a scalar. Oh, sorry. Yeah. Sorry, you're right. If x is bounded by a function of y, you integrate this, you plug in the bounds, you're gonna end up with the square root of y. That's not a scalar with respect to y. So that's why this theorem won't, this property doesn't work if you don't have scalar bounds. Okay. Let me have you guys, yeah, I think I could do it. You guys want to try one? Practice try one? Yeah. My gut says I need you guys to try one. Your eyes look like you want to. I've been talking to them. So I'm going to kind of make one up on the fly here, okay? Let's see what happens. All right. So I'll say like this: evaluate this integral here. Where D is, and I'll just sketch the region here. Let me see if and I'll just sketch the region for you. So this is the region here. Okay. So try it out. So this is region D. Try to evaluate this double integral using polar coordinates. You could do all of these in rectangular coordinates. It's just really hard. Try to do it in polar coordinates. So try it out. Oh, can you see that?
So we can just half of the circle?
Yep, it's just half of the circle. Okay. That's what makes it a little harder. Think of the laser. Think of the laser for your thetas, okay? Think of thetas could be negative as well. Don't forget about that. Negative, negative. I guess I'm showing you that boundary. Here, I'll go like this. That's the equation of this circle here. Yeah. Thank you. But D is only that region. Only half of that part. I don't know. I just made it up.
Just R here, so R beyond the table, and the theta is derived from negative allowed to.
Yep. So setup looks good.
So just. Okay. So like for the questions we did here, so we didn't we only have scalar bounds. Like for polar coordinates.
No, right now, yes, but the next part is, I'm gonna show you that now. It gets a little harder.
Okay, waiting for that.
Yeah, yeah.
That'll be last.
What's up, bro? You actually want to do that. If you do 3 pi over 2, then that is this part. Pi over 2 to 3. You can't do 3 pi over 2. You wouldn't be able to do this. Yeah, you can't do that because this number is bigger than that. Yeah, so yeah, exactly. You're gonna have to use a negative. What's your R? Oh shit, my theta. Because what this is saying is that by doing that, you're saying R is between this, but this number is bigger than this. This inequality is incorrect.
Why can't you just
It'd be like saying something like this. Yeah. I guess yes. Yes. We just might forget the name. But technically, yeah. I think they only do Jeopardy once.
唔係總體上，唔係總體上咧。如果呢個識搞圖咧，咁佢其他即係你教個科咧，即係肯定高年個人係一樣噶嘛。我以前就係咁樣諗㗎，我試過唔係點解係中文嘅？
Here. I think you showed up a little late. That's like part of what we did at first. Beginning of class. This is our region. All this algebra.
係啊，其實我選課嘅時間都係根據我之前可唔可以記到新，我而家要記到好多。
This is an easy one, right?
暑假記得到新，但係我半年之前我記唔到新。
The mild one. It gets spicier.
因為我下個
Okay, guys, let's see. So your R here should go from 0. What is the radius of the circle? 2 units. So R goes from 0 to 2. And then here's the whole discussion we had with the theta. You can't have 3 pi over 2 and then pi over 2 like that. Because this is an inequality. 3 pi over 2 is not less than pi over 2. So instead, we use the coterminal angle, negative pi over 2. Okay? So that ranges like that. Okay? My laser starts touching the region here, and then it ends touching it up there. So then this bad boy has theta ranging from 0 to, negative pi over 2 to pi over 2. The R will go from 0 to 2. What did you guys convert this to?
R squared.
R squared, and then the dA pops out that R theta. Scalar bounds, R cubed times 1. So you can split it up into a product of 2. And then with just R's. And I believe you guys should have got 4 pi. Okay? This guy here would be theta times pi over 2 negative pi over 2. So it's pi over 2 minus negative, so it becomes plus. So this gives you pi. And then what did you guys get here? It was 1/4 part of the 4 is 0.
0 to 2.
0 to 2. That changes like a lot. So then what is that? 16 over 4? Which is 4. So yeah, so you get 4 pi. What? Okay, so now the question is, will it always be this magically easy where my pounds are numbers? Yes or no? Okay. So I want to explore that real quick. Let me show you a picture first. Shit. Okay. All right, so let me show you a picture, which is this bad boy. So the reason these were always scalars were because my lower bounds for R were always perfect circular arcs. But that's not always the case, right? I can have a region where my lower bound for R is some other non-circular curve and another non-circular curve. It could be polar curves, like what we were doing on the warm-up. So I can have R be bounded below by some polar curve expressed as a function of theta. And I can have the upper bound for R expressed as some other function of theta. And so, luckily, for the problems I gave you on the homework, your theta will be bound by scalars, always, okay? But there's also more complicated ones where theta isn't always bounded by, which they might sneak in chapter 16, okay? So it's basically going to be the exact same thing we've been doing when you convert from rectangular to polar, except that now your R's are going to be bounded by functions of theta. That's the only difference. So we won't be able to use this rule though. Okay? So that's the main difference. So That part though just makes it like the difficulty level go a little bit higher than usual. So I want to kind of, I want to train your eyes to those scenarios, and I'm gonna give you 3 examples. We're not gonna like do the actual integral, but we're just gonna do more of a setup, so that you can train your eyes for bounding your R's and your theta's. Okay. So here's some challenges of double integrals and polar to make sure that you're aware when you're studying all this stuff. Meaning, like when the third exam starts coming around, you're like, what do I have to study for this section? These are the things you need to study. The first one is finding the polar equations of boundaries. What is the h of 1 theta and the h of 2 theta that is in the picture? Once you find the polar equations, is then kind of knowing how R is bounded by it. Seeing the bottom one bounds R and the top one bounds R. And see how that happens. Which one bounds R above, which one bounds R below. And then determining the angles so that your theta will be bounded by alpha and beta. That laser analogy that I keep telling you guys is going to be very helpful. So you kind of already did this one, right? Notice that there was a little bit of like a new thing in your head where you had to think about this thing, the bounds here. It was new. Right? That's what made this problem, in my opinion, hard with the setup, was the theta. So let me give you 3 other types of boundaries. And I want you guys, all I want you guys to practice is finding the bounds. Don't worry about the integral part. I just want you to practice finding the bounds. Okay? We'll do it together. But you guys are going to help me. So 1, 2, 3. All right, so here's the first one. It's going to be the one we did in the beginning of class. So it's going to be the circle. Yo, my circle game's on point today. Okay, so here's 2, here's 1. And then this is R equals 2 cosine theta. And D is the entire region, the entire circle. Example number 2 is very similar to this one, but there's also a little circle inside of it. Where this is R2 cosine theta, this is going to be R1 cosine theta. And your region is going to be this part of it. Like that. And then the third example is going to be a pedal. So this one's going to be harder to draw. It's a pedal where the pedal kind of is between these 2 angles like this. This pedal will have 4, it'll have 4 pedals, but right now the region D is only that one petal. Yeah. Okay, let me stop it. Let's draw that real quick. Yeah. Oh, yes, you do. Two. I kind of want to make them all look kind of similar with R, so you guys could see how they can be a little tricky. All right, you ready? You still drawing? Okay. All right. So remember, you're trying to find R and theta. Your laser starts at the origin. Okay? When my laser was on the one that you guys just did, and I shot out my laser, no matter the angle that the laser was at, the biggest R was always 2, and the smallest R was always 0, no matter the angle. No matter where that laser is being shot, R was always the biggest 2 and the smallest 0. Okay? Notice that for this one, if my angle is 0 radians, R, the biggest it'll be is here, 2 units. But if I have some other angle, that R is definitely not 2 units. It's smaller. This angle will have R be over here. So as I vary my theta, my length of R is not always going to be a scalar, right? So what do you think will be the upper bound for R? Will it be 2? It's going to be whatever this curve tells you R is, 2 cosine theta. But for every angle, what's the smallest R can be? 0, right? So R will be in between 2 cosine theta and 0. In my opinion, this is the one big leap for you guys, is understanding when it's that and not 2. Okay, and what I want you to think about is, for every angle, is R always a length of 2? If the answer is yes, then yes, right? But if it's not, for every angle, then it's going to be bounded by a polar equation. All right, here's the other hard part. Okay, here it's very obvious that theta, like if I shoot my laser, right, the smallest angle that it starts hitting the region is at -π/2, and then it'll vary the laser until it hits π/2, and then it doesn't touch the region anymore, right? All right. My laser here at 0 radians, it's definitely touching the region, right? What's the smallest angle where it'll touch the region? So are you guys saying that theta can't go negative? It can, right? And it's still going to hit the circle. But what's the smallest angle? -π/2. And that's where it's kind of new. It's kind of weird, because as this green line keeps going towards -π/2, it's going to touch it until you get π/2. What is R at π/2 though? 0. But it's still technically touching the circle. Okay? What's the biggest arc, biggest the theta can be? Positive π/2. That right there, that step that we just discussed, God, that was so hard when I first taught this class.
How can we do from 0 to pi?
The reason you don't do 0 to pi is because after π/2, R is going to be some value over here that's not going to touch your circle anymore. Yeah. Yeah, once you're over here, your R's won't stretch anywhere that will be on the circle.
Oh,
Yeah. So your theta is going to be between positive π/2 and negative π/2. Okay. Okay, now let's go to this one. Again, laser starts at the origin. Let's say I pick this angle here. If I pick this angle here, I'm not on the region, and then boom, I'm on the region until I get here, then I'm on the region again. Okay? Maybe maybe I have a different angle. Maybe the angle now is here. I'm not on the region, and then boom, I'm on the region, and then I'm on the region right there. So for all those angles, what's the biggest R stretches to? 2 cosine theta. What's the smallest it stretches to so that it's still on the region? So it's cosine theta. It's not 0 anymore, right? Because if it's 0, it's from here to here. We're not going to be on the region. So this guy here is going to have R stretch from 2 cosine theta to just 1 cosine theta. What about the angles though for the laser? It's going to be the same as this one. Okay. Now let's do this one. I pick an angle and I'll stretch my R. It stops here and it started there. Maybe I pick another angle and it's here, right there. So what's the biggest R is going to be? The curve, right? The curve. Cosine 2 theta. What's the smallest that it can shrink down towards? 0. Okay. Now notice, if I'm somewhere here, let's say this angle right there, I plug that angle into this function. Let's say it's like 60 degrees. What's that? Pi over 3? You put that in your calculator, that's going to give you some positive answer. Okay? So for that angle, will I have a point anywhere on my region? No. So in this case, the angle doesn't go all the way to pi over 2. It's going to stop at whatever like this funky, weird, asymptotic angle thing is there. Okay? You guys see the green radius here? At that point, notice that as I keep rotating it, it's going to shrink until I get to whatever this angle is. R will have to be 0 at that angle. So the way you're going to find these angles is by using the function to see when R will equal 0. Okay? So to find the angle bounds for theta, it'll be when R is equal to 0. And so you get your function here. You get your function, your full equation, and you're going to set R equal to 0. Do a little bit of trig. For what angles does cosine equal 0?
Yeah, plus or minus pi over 2.
Plus or minus pi over 2, right? So this tells you if you use a calculator and you do cosine inverse, it's only going to give you one angle. It's not going to give you 2. So you do have to use a little bit of your knowledge of trig. Yeah.
Since there are 4 pedals, can you also just figure out that it's pi over 4 instead of 2 and that? Because it.
Yes. Yeah. But you know, sometimes the pedals are like rotated, so the angles might differ. But yes, in this case, yeah. So this tells you that your 2 theta is going to have to equal, what did you guys say? Plus or minus pi over 2. Divide both sides by 2. And theta is going to have to be plus or minus pi over 4. So that tells you the bounds for theta. That problem is this. Okay, where it's a little bit harder to figure out the angles. You have to do a little bit more side work. So then your theta is going to be bounded by positive to negative pi over 4. So I'm going to leave these 3 examples. Okay. I have 2 problems for you that I would like you guys to try. And then just be careful when you're doing your maths. So here, let me have you guys try these worksheets, and then the solutions will be posted in the notes. Sam, can you just give one second so that Sosa doesn't have to? Yeah, you'll have to do for more complicated ones. We'll do one later on in chapter 16. You might have to do like the angles will be like you have to use tan inverse, or you have to use inverse sine or inverse cosine. Yeah. No, because remember when you divide by 2, you're going to multiply it by the reciprocal. Yeah. So then the 2 becomes 1 over 2. Thank you. Does anybody, did I miss anybody? Oh, they're coming. All right, guys, so try it out. For number 1, you're just setting up the integral, okay? You don't know the actual function, f. It's just some arbitrary function f. Say it again?
It's the most complicated way to put yourself.
Yeah, the changing it to polar will help. Pause it. All right, let me just show you 15.5 is really short. All right, so here's the main idea. You're going to have a surface of your function above some region, and we're going to basically split up that region into smaller subregions. Pick a point, a corner point for each of those subregions, and you're going to plug that point into your function. Okay? Hopefully it lets me show you let me see, hold on. Spotlight, here you go. You're going to get that point, you plug it into your subregion, into your function, sorry. And then this part you're not going to be expected to do, okay? But basically theoretically what ends up happening is you get that point and you're going to find a little tangent plane, which is a little tangent parallelogram there above this little subregion. And then if you guys see this darker blue surface area underneath the pink parallelogram, that little blue one is the surface area on the region above your subregion. But that dark blue surface area is approximately equal to the area of the small little tangent parallelogram. So then what you're going to do is you're going to approximate it with the area of that small parallelogram. So here's a zoomed out picture. That parallelogram is going to use a tangent vector A and a tangent vector B, where these are the tangent vectors to the surface. And then we learned, and I think it was in section 12.2, I think, 12.4, where we did cross product, that the cross product of these two vectors, you take the magnitude, and that is the area of the small tangent parallelogram. And so then the idea is, how do I find these tangent vectors? Well, it's going to be the tangent vector as x is changing in the x direction, and then b will be tangent in the y direction. We looked at those vectors in the past chapters. We called them vx and vy. But I want, for a, I want the x component to be a length of delta x. So we're going to have to do a scalar multiplication of delta x to get a. And I want the y component for the other vector to be of value delta y. So we're going to do a scalar multiple to get that desired value. And so basically we take the cross product of these two fancy vectors. We end up with this pretty vector here that where each component has a multiple of delta x times delta y, which is really just delta a. So we factor it out, and notice we end up with this pretty partials here with a 1 here for z. Take the magnitude of this guy, and then we end up with this square root expression with delta a. And so basically, that represents the area of all these small little parallelograms, these tangent parallelograms. So we add them up, split it up, go to let these subregions go to infinity, like we've been doing. And then that ends up giving us this surface area formula with a double integral, where if you have a surface of your function f, and you have your partials that are continuous on this region, then the surface area over that region D is the double integral over D of the square root function dA. And so notice that it can get a little nasty here if you stay with x's and y's because of trig substitution. So when you end up doing these in this section, whoops, you're gonna, I showed you, you'll see an example here that we didn't end up having time to do, but you're trying to find here this paraboloid facing up. It's being sliced by this plane at z equals 9. We're not being asked to find the volume between the plane and the paraboloid. We're being asked to find the surface area of just that part of the paraboloid. Okay. Notice the paraboloid intersects the plane where z equals 9. So we end up with a circle above here, on top here. We end up with a circle of radius 3. So because we have a circle, we switch to polar. Okay. And then the function is the function of the surface that we're trying to find the surface area, which is the paraboloid. And so that's what we're going to define to be our f. And so to do the surface area, I have to take the partials of that, square them plus 1, so we end up with this expression here to find the surface area. But when we switch to polar, this just becomes 4 times x squared plus y squared, so it becomes 4r squared. And then I just use my bounds for r and theta. And then you do a whole bunch of, then you actually integrate. Okay, you could take a look at that later on your own. And then I end up with my surface area. Notice I put units squared on purpose so that you forget it's not volume. It's representing the surface area of this piece of the paraboloid. All right, guys. Peace.